Live, you can continue. Please, screen is yours.
Hello everyone, I'm Giorgi Tomadze, student of Tbilisi State University. Thanks for the opportunity to read the work. Our today's report is about radio hacking related problems and methods to solve it. It's a common idea that in the 21st century any person has daily contact with technologies that work on radio waves. The radio wave itself is electromagnetic radiation, the wavelength of which is longer than infrared radiation in the electromagnetic spectrum. As technology relies heavily on radio waves, cyber attacks have increased. Today we will discuss the dangers, share knowledge based on practical trials, and show you a small demonstration. The history of radio waves begins at the end of the 19th century, when Heinrich Hertz first demonstrated the existence of electromagnetic waves. Radio hacking usually involves the unauthorized manipulation and interference of radio signals. It includes the exploitation of vulnerabilities in radio systems. Our report today is about cybersecurity in aviation. The modern aviation system relies heavily on radio technologies, which are essential for the efficient operation of this complex system. Most of the system uses the very high frequency range of radio frequencies. This system includes the following. First, voice and written communication between the air traffic controller and the pilots, and second, the use of ADS-B and its integral part GNSS. Using them, it becomes possible for the aircraft to broadcast its position, altitude, and other important data. This information is critical for air traffic controllers, as the above has serious vulnerabilities that could lead to dire consequences for an attacker. An attacker can impersonate the signals transmitted by the aircraft and pretend to be a flying object, or change the data transmitted by the authentic aircraft. This action could cause critical damage to aviation infrastructure and airflow. In addition, other radio signals are used in the aviation field, although they are outside the scope of our presentation. This photo, based on an ADS-B source, shows an aircraft that was actually destroyed by bombing on February 27, 2022, during the Russia-Ukrainian war. The photo was taken a few days later. It was an ideological cyber attack. For the demonstration, we will use the device HackerF. HackerF is a versatile software-defined radio platform known for its flexibility and open-source design. It allows users to explore and experiment with different radio frequencies and provides reception and transmission over a wide range of radio signals. The demonstration is held in controlled environments. Play the video here. In this video, the transmitting device and antenna are marked with red frames, and the receiving device and antenna are marked with red ones. At the push of a button, an attacker would launch a kind of ADS-B attack, sending a digitally encoded signal containing data from non-existent aircraft. Then the receiving device momentarily decodes the signal and displays the non-existent aircraft data on the screen. You will agree that we rarely find such a person who doesn't have contact with GPS. GPS is an American satellite system that belongs to GNSS. In fact, we also use these other systems such as Galileo, GLONASS, Beidou, etc. We use this means of navigation in our daily life, but we might be surprised how dangerous a cyber attack on it can be. The principle of its operation at first glance is quite simple. It works by using a network of satellites orbiting the Earth to accurately determine a position on the surface of the planet by calculating the distance between the receiver and multiple satellites to define a specific location in three-dimensional space based on the time of the signal and the known position of those satellites. Today, a GNSS receiver is available to everyone. All types of GNSS satellites broadcast on different channels, namely L1, L2, L3, L4, and L5. Information is broadcasted from GNSS satellites at a speed of 50 bits per second. It transmits satellite orbit data and satellite time, which is indispensable in the case of civil aviation. GNSS vulnerabilities combined with radio frequency interference are causing concern in the aviation field. This appearance of GPS signal is becoming increasingly common in civil aviation, especially in politically tense areas. There can be many reasons for this, but it is likely that they are provoked, since signal suppression is no longer a difficulty today. Although jamming is very dangerous and may happen occasionally, a spoofing attack is even more dangerous and predictable. GNSS spoofing is a technique in which false signals are transmitted to the receiver, causing it to calculate an incorrect location. It can be falsified by generating radio waves that mimic authentic GNSS signals, which sends false information to the receiver. GNSS spoofing increases threat risks because its use. It can be used to fool navigation systems, disrupt critical infrastructure, or interference the path of autonomous vehicles and aircraft. In 2010, a similar attack was carried out at the Hanover airport by accident. Although this all sounds incredible, the case has already been investigated and it has been determined that the source of the fake signal was the ongoing test in a nearby hangar. This once again shows how easily it can be to spoof signals like this. Since the aircraft positioning system was fooled, the ADS-B data was automatically changed accordingly. In 2018, Russia accused the US of falsifying the authenticity of the drone and using it to attack a Russian airbase in Syria. Also, in the past few years, there have been many location spoofing incidents near the Russian border, and the drones are believed to have been placed at nearby airports. Simple and relatively complex attacks can be carried out on GNSS. In simple attack, the attacker suppresses the authentic signal and broadcasts its own fake signal, causing the receiving device to tune into his signal. Detecting and avoiding such a simple attack is not very difficult, since the fake and real signals will not be synchronized, and this can be easily detected by software. In the case of more complex attack, the attacker tries to covertly convert the receiver from an authentic signal to a fake one. For this, he must first mask the authentic signal with a fake signal so that all indicators are initially similar to the authentic one, and then change it in his favor. The greater the involvement of technology in modern life, the greater the likelihood of insecurity increases. Naturally, technological regression can't help us in this, although there must be certain aspects that must be strictly protected. We've already explained the dangers of those attacks. Now we can talk about the methods of solving them. First, to prevent GNSS spoofing, we all think of encrypted data exchange. But with today's technology, that's practically impossible. Because of the distance, they have to broadcast at a low, very low frequency, which doesn't allow the implementation of mass encryption, unlike the military unit. The military sector is capable of encryption communication only because they use the same encryption algorithm that the receiver uses to decode the signal. All receivers use the same key. Current GNSS systems only allow communication to be encrypted with symmetric algorithm. This is unsuitable for civilian use, as storage, distribution, and management of the different encryption keys is practically impossible. In fact, one of the appropriate ways of protection may be a verification mechanism. The use of additional sensors, such as inertial navigation systems or alternative positioning technologies, play a crucial role in the protection of navigation systems. By combining data from multiple sensors, including GPS, these systems can maintain accurate positioning information, even if difficult environments or when the GPS signal is interrupted. Additional sensors provide a backup mechanism that is responsible for the continuity of navigation and protects against potential threats, such as GPS spoofing or blocking. We can consider multi-frequency receiver as another protection mechanism. Multi-frequency authentication in GNSS allows us to use different frequency signals, such as L1, L2, and L5. This approach enhances accuracy by reducing the effect on environmental factors, such as the ionosphere, blurring the signal and resisting interference and spoofing attempts. Multi-frequency authentication contributes to the reliability and security of GNSS, making it valuable for applications that require accurate and reliable positioning information. We may also have active monitoring of the signal quality as a version, which ensures detection of the changes in the signal, anomalies, and unauthorized interference. ADSB spoofing solution methods. For example, by using message authentication, we can make sure that the data is not forged. Authentication of the message can be an electronic cryptographic signature with which the recipient will confirm the integrity of the message. Or the easiest way, let's go back to the compass method. Okay, in this presentation, we explored the dark side of radio technologies, delving into the dangers of GNSS and ADSB spoofing. However, by taking the necessary actions and promoting cooperation, we can strengthen the security and reliability of these important systems. Thank you for your attention.
Thank you very much for your presentation. It was interesting to hear what happens in the dark side, so thank you for that. And now we have our next presenter, Giorgi Akhalaia.